If you have one continuous unspliced grounding electrode conductor, it must be sized for the largest grounding electrode required among all the electrodes connected to it. For example, if you have a 200 amp service, you would need to use a number 4 American wire gauge copper conductor for the unspliced grounding electrode conductor, even if you are connecting it to a water pipe, ground rods, or rebar. If you run separate grounding electrode conductors, you can run a number 4 American wire gauge to the water pipe and a separate number 6 American wire gauge from the bus to the rods or rebar. This is because section 250.66 of the National Electrical Code allows connections to made electrodes such as ground rods or rebar to be no smaller than number 6 American wire gauge copper. It is possible that the lack of Cadwelled 1 shots for number 6 American wire gauge is due to the fact that number 6 American wire gauge is the minimum size allowed for connections to made electrodes. As such, there may not be a high demand for Cadwelled 1 shots for this size conductor. Rebar does not qualify as a made electrode under the National Electrical Code. Made electrodes are defined in section 250.52 C and D of the National Electrical Code as electrodes that have been manufactured for the purpose of grounding and electrodes of conductive material that have been driven, embedded, or otherwise installed in the earth, in concrete, or in masonry for the purpose of grounding. Rebar is a type of reinforcing bar used in concrete structures, and it is not specifically manufactured or installed for the purpose of grounding. When dealing with grounding electrode systems and grounding electrode conductors, it's crucial to understand the requirements outlined in the National Electrical Code to ensure safety and compliance. Let's delve into the specifics of sizing grounding electrode conductors and how they relate to different types of grounding electrodes. Firstly, let's clarify the scenario where you have one continuous unspliced grounding electrode conductor. The code dictates that this conductor must be sized appropriately for the largest grounding electrode it connects to. Consider a situation where you have a 200 amp service. In this case, you would indeed need to use a number 4 American wire gauge copper conductor for the unspliced grounding electrode conductor. This requirement holds true even if you are connecting to various grounding electrodes such as a water pipe, ground rods, or rebar. The rationale behind this is to ensure that the grounding electrode conductor can adequately handle any fault current that might flow through the grounding system. Now let's address the alternative scenario where you choose to run separate grounding electrode conductors to each grounding electrode. In this case, you have more flexibility in sizing the conductors. You could run a number 4 American wire gauge conductor to the water pipe, as this connection might require a larger conductor size based on the service entrance conductor size. Simultaneously, you can run a separate number 6 American wire gauge conductor from the bus to the ground rods or rebar. This approach is permitted because section 250.66 of the National Electrical Code specifically allows connections to made electrodes, which include ground rods and rebar, to be no smaller than number 6 American wire gauge copper. This provision recognizes that the fault current contribution for made electrodes is typically lower, justifying the use of a smaller conductor. Let's explore the possible reason for the limited availability of Cadwelled 1 shots for number 6 American wire gauge conductors. Cadwelding is a method of creating a permanent, exothermic weld between conductors, and one-shot kits simplify this process. The fact that number 6 American wire gauge is the minimum size allowed for connections to made electrodes could explain the scarcity of these kits. Since number 6 American wire gauge is already the smallest permissible size, the demand for specialized Cadwelled kits for this specific size might not be substantial enough to warrant widespread manufacturing. Instead, installers might opt for alternative connection methods or use generic Cadwelled kits that accommodate a range of conductor sizes. It is also important to distinguish between different types of grounding electrodes, especially the concept of a made electrode. According to the National Electrical Code, rebar does not qualify as a made electrode. The code defines made electrodes in section 250.52 C and D as electrodes that have been manufactured for the purpose of grounding and electrodes of conductive material that have been driven, embedded, or otherwise installed in the earth, in concrete, or in masonry for the purpose of grounding. Rebar, on the other hand, is primarily a reinforcing material used in concrete structures to enhance their tensile strength. While rebar can serve as a grounding electrode when it meets specific requirements, it is not inherently considered a made electrode because its primary function is structural rather than grounding. To further clarify, let's outline the specific requirements for grounding electrode conductors as per the National Electrical Code. The size of the grounding electrode conductor is determined by Section 250.66, which provides a table to correlate the size of the service entrance conductor or equivalent area for parallel conductors with the required size of the grounding electrode conductor. For instance, if you have a service entrance conductor made of copper and its size is 2/0 American wire gauge or smaller, then the minimum size of the grounding electrode conductor would be number 6 American wire gauge copper. However, if the service entrance conductor is larger, say 3/0 American wire gauge to 350 kc mil, then the grounding electrode conductor would need to be at least number 4 American wire gauge copper. Remember that these are minimum sizes, and you might need to upsize the grounding electrode conductor based on other factors such as the presence of multiple grounding electrodes or specific requirements of the local jurisdiction. When connecting to made electrodes, such as ground rods or ground plates, Section 250.66 allows for smaller grounding electrode conductor, but not smaller than number 6 American wire gauge copper. This exception recognizes that the fault current contribution from made electrodes is generally limited by their impedance to earth. However, it's crucial to ensure that the connection to the made electrode is mechanically sound and electrically conductive, which is where methods like CAD welding come into play. Let's address the question of why you might predominantly see CAD weld one-shots for number 6 American wire gauge conductors. This could be attributed to several factors. Firstly, number 6 American wire gauge is a commonly used size for connecting to made electrodes, as it represents the minimum size allowed under Section 250.66. Secondly, CAD welding offers a reliable and permanent connection, which is particularly important for grounding electrodes that are often buried underground or encased in concrete. Thirdly, the availability of one-shot kits simplifies the CAD welding process, making it more convenient for installers to create consistent and high-quality connections. However, it's important to note that CAD weld one-shots are available for other conductor sizes as well, depending on the manufacturer and the specific application. Now, let's explore the role of rebar as a grounding electrode. While rebar is not classified as a made electrode, it can be used as a grounding electrode if it meets certain conditions outlined in Section 250.52(a)(3) of the National Electrical Code. This section allows the use of a concrete encased electrode, which consists of at least 20 feet of 1/2 inch diameter or larger rebar encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. When rebar is used as a grounding electrode in this manner, it becomes part of the grounding electrode system and must be connected to the grounding electrode conductor. The size of the grounding electrode conductor connecting to the rebar would be determined by Section 250.66 based on the size of the service entrance conductor. It's important to note that the connection to the rebar must be accessible and made using approved methods such as listed grounding clamps or exothermic welding. Let's discuss the advantages and disadvantages of using a single and spliced grounding electrode conductor versus multiple, separate grounding electrode conductors. A single and spliced grounding electrode conductor offers the advantage of simplicity and a direct path for fault current to flow back to the source. It also reduces the number of connections in the grounding system, minimizing the risk of loose or corroded connections. However, the requirement to size the conductor based on the largest grounding electrode can result in a larger and more expensive conductor. Multiple, separate grounding electrode conductors offer the advantage of flexibility in sizing the conductors based on the specific requirements of each grounding electrode. This can result in cost savings, especially when connecting to made electrodes that allow for a smaller conductor size. However, multiple conductors increase the number of connections in the grounding system, which can potentially increase the risk of connection failures. It's important to carefully consider the pros and cons of each approach and choose the one that best suits the specific application and budget. Let's address the common misconceptions about grounding electrode conductors and grounding electrodes. One common misconception is that the grounding electrode conductor is solely responsible for protecting people from electric shock. In reality, the grounding electrode conductor is primarily intended to provide a path for fault current to flow back to the source, allowing the overcurrent protective device such as a circuit breaker or fuse to trip and clear the fault. The equipment grounding conductor, which runs with the circuit conductors, is the primary means of providing a low impedance path for fault current to flow back to the source, thereby minimizing the voltage on metal parts that could be touched. Another misconception is that a larger grounding electrode conductor always provides better protection. While a larger conductor can handle more fault current, it doesn't necessarily improve the effectiveness of the grounding system if the grounding electrodes themselves have high impedance to earth. The impedance of the grounding electrodes is a critical factor in determining the overall effectiveness of the grounding system. Let's delve deeper into the importance of proper grounding electrode installation. The effectiveness of a grounding system depends not only on the size and type of grounding electrodes and grounding electrode conductors, but also on the quality of the installation. Improperly installed grounding electrodes can have high impedance to earth, which can significantly reduce the effectiveness of the grounding system. For example, ground rods should be driven deep enough into the earth to reach moist soil, and they should be spaced at least twice their length apart to minimize the overlapping of their effective grounding zones. Connections to grounding electrodes should be made using approved methods such as listed grounding clamps or exothermic welding to ensure a reliable and low impedance connection. The grounding electrode conductor should be protected from physical damage and corrosion, and it should be routed as directly as possible to the grounding electrodes to minimize impedance. Let's explore the role of supplementary grounding electrodes. In some cases, a single grounding electrode may not provide sufficiently low impedance to earth, especially in areas with dry or rocky soil. In such situations, supplementary grounding electrodes can be added to improve the effectiveness of the grounding system. Supplementary grounding electrodes can be installed in various configurations, such as ground rod rings, ground grids, or chemical ground rods. Ground rod rings consist of multiple ground rods interconnected by a bare copper conductor, forming a ring around the perimeter of the building. Ground grids consist of a network of interconnected bare copper conductors buried in the earth, providing a large surface area for contact with the soil. Chemical ground rods contain chemicals that leach into the surrounding soil, improving its conductivity and reducing the impedance of the grounding electrode. Let's discuss the requirements for bonding other metal objects to the grounding system. In addition to grounding electrodes, other metal objects in and around a building should be bonded to the grounding system to minimize the risk of electric shock. This includes metal water pipes, gas pipes, metal building frames, and metal equipment enclosures. Bonding these metal objects to the grounding system ensures that they are at the same potential as the earth, reducing the voltage difference between them and other grounded objects. Bonding is typically accomplished by connecting a bonding jumper from the metal object to the grounding electrode conductor or to a common grounding busbar. The size of the bonding jumper is determined by section 250.66 based on the size of the service entrance conductor. Let's delve into the specifics of grounding electrode testing and maintenance. Regular testing and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding electrode testing involves measuring the impedance of the grounding electrodes to earth using a ground resistance tester. Test results should be compared to the recommended values to determine if the grounding system is performing adequately. If the impedance is too high, corrective action should be taken, such as adding supplementary grounding electrodes or improving the soil conductivity. Maintenance of the grounding system includes inspecting connections for corrosion or looseness, protecting grounding electrode conductors from physical damage, and ensuring that grounding electrodes are properly buried and protected. Let's discuss the impact of changes to the National Electrical Code on grounding requirements. The National Electrical Code is updated every 3 years, and these updates often include changes to grounding requirements. It's important to stay informed about these changes and to ensure that grounding systems are designed and installed in accordance with the latest edition of the code. Changes to grounding requirements can be driven by various factors such as new technologies, improved understanding of electrical safety, and the need to address emerging hazards. For example, recent editions of the National Electrical Code have included new requirements for grounding photovoltaic systems and electric vehicle charging stations. Let's touch on the role of professional electrical engineers in grounding system design. Designing an effective grounding system requires specialized knowledge and expertise. Professional electrical engineers can play a crucial role in ensuring that grounding systems are designed and installed correctly. Electrical engineers can perform calculations to determine the appropriate size and type of grounding electrodes and grounding electrode conductors, taking into account factors such as soil resistivity, fault current levels, and the presence of sensitive electronic equipment. They can also develop detailed grounding plans and specifications, and they can oversee the installation and testing of grounding systems. Finally, let's remember that grounding is a critical aspect of electrical safety, and it's essential to follow the requirements of the National Electrical Code and to consult with qualified professionals to ensure that grounding systems are designed and installed correctly. A well-designed and properly installed grounding system can protect people from electric shock, prevent equipment damage, and minimize the risk of fire. By understanding the principles of grounding and by adhering to best practices, we can create safer and more reliable electrical systems.